Alright, another draft physics video presentation. Just deal with a single subject here, the two slits, the single slit, the diffraction gradient, the idea of wave interference in its the simplest form of it. The experiment that illustrates it, the one they call the nail in the coffin experiment, Lewin, Sakar, Feynman. No, Feynman didn't say that. But anyway, this is, the jargon is that the two-slit experiment just makes it impossible to imagine any other theory being possible, that it has to be a wave, blah, blah, blah. So this is the experiment that got me into this whole thing 10 years ago, in the sense that the explanations, the Copenhagen, the many worlds, the whatever the other thing is, the Feynman random is part of the God does play dice with the universe. That's Feynman's answer. God actually does play dice and things are actually randomized. Silly in my opinion, unacceptable as answers, too incomplete, no way to even imagine these waves interacting, just doesn't make any sense. So I went looking for, there has to be a better answer, and yes, this took me 10 years to find it, and it's so simple in the end that you're saying, there's got to be this is more than just a failure of communication, or it's a failure in thought process, because clearly science really wasn't looking to find the right answer, they wanted to get to their answer. And so any road that goes where they want to go, they don't really care. It's not paved. They don't care that it's, you can't survive the trip because there's no bridge across the cavern. They just, the map isn't the territory. What they're imagining isn't what the physical world. They're not correlating the two very well. And they never really picked at any of this stuff. So anyway, that's enough commentary. So it is a critical experiment, and I would argue, just like they said it was nail in the coffin evidence, I would argue that, well, let's put this down as nail in the coffin evidence that quantum mechanics is a fundamentally flawed perspective. Okay, so the idea is this: first you have to know something about what a photon is. So conventional physics argues that some sort of fields are doing some sort of field thing. Okay, some field is doing this with an amplitude change, and some field is doing this, and that this thing is moving in a direction at the speed of light, whatever that thing is. These fields vibrating in two dimensions: a magnetic field, an electric field, which I would argue there's no evidence these things even exist. So anyway, that's their notion. They don't really talk about ray length ever. Obviously the field would have nodes, and the nodes would have, these vibrations in the field, whatever they are. Clearly you can have a number of them. They really don't talk about that at all. And there's a thing called polarization, which gives it a dimensionality, an amplitude in these directions, and somehow it has two polarizations because there's two fields, but I don't understand that part. It doesn't make any sense, because what polarization really is saying is that something's traveling at you like this piece of chalk. It has a direction, and it can come at you this way or come at you this way. Now, two fields can't be constantly rotating or whatever they would have to do, and obviously the two fields would have to be in different polarizations, and there's no evidence of that either. So anyway, just as a background, you don't really need to understand photons properly to understand my criticism of the two-slit analysis, but I would argue that photons are created just like a radio signal. Electricity has to travel an antenna of sorts, and the photon is created in little bits. And so little bits, obviously the first bit that shoots out gets further in a unit of time, over a period of time. So the photon is basically just created the same way the frequency is created in antennas, and it just really has to do with how fast electricity can move through the antenna. And so atoms create photons by electricity traveling through, and the pieces of the photon are just the nodes of their wave, these nodes that would be in their wave. You could just understand them as being actual bits. The actual bits, let's do it from top to bottom, would travel. They'd be in different frequency. The frequency and the polarization, that is the difference in the position of the atoms, the spacing would be the same as the difference in the frequency, that is the distance between the atoms, and so the two would be correlated. Polarization would be proportional to frequency or wavelength. So this is what travels through space, is something moving this way. They're all little bits moving the speed of light. They're in a frequency distance from each other that's consistent, and they have a length. And so the argument is the human eye can pick up 6 to 9 of those things, and the human eye can see it. If it has 3 or 4, then a frog can see it. Okay, so we have a different definition of what a photon is based on what instrument or what eye is looking for it. So clearly, this, you can understand that that's really the difference, is that how you're measuring it. And the fact is that it matters how long it is. Frogs see photons we don't see. Fact. Why don't we see them? Well, we don't see them because there's not enough energy. Anyway. Alright, so this slit experiment, as traditionally drawn by the professors, they will totally, in a single slit, they'll totally ignore the fact that you can have pattern, and they basically want to just say, that this happens, that you have this big diffraction pattern, and you have these little nodes, and they're really unimportant. Well, that only happens when the width of the slit is very small. That is, it has to be just 2 wavelengths. Okay, so 2 of the frequency notches in distance. So this is 500 nanometer light. Okay, so you would argue that then it's 500. You're talking about 1 micrometer of for 2 wavelengths. So a micrometer slit will produce this pattern, but you'll get 1 little node. But obviously, if I make this wider, like 1/10 of a millimeter or some other bigger number, I'll have many frequencies in here. I'll be able to fit many wavelengths inside there, and I will create many of these little bars. So instead of the pattern looking like that, the pattern will look like the center one will be a little bit bigger, and then there'll be a light spot and a light spot and a light spot and a light spot. Now, an obvious thing they never fixed. So they've had 100 years, 200 years analyzing this experiment, and they've never really understood that it's really their math even doesn't work, because in terms of predicting where these locations will be, because this is a distorted perspective. So just like you can't project a movie onto a flat screen, a very wide screen movie, if you project it on a flat screen, you'll get tremendous distortion. So what happens is the further away you go, these things start getting longer and longer. Okay, you can see all of it. So there's a lot of distortion in your view, and your mathematics isn't predicting what it is, because it's predicting it cast on a wrong surface. So the stretching isn't part of the math, because you're projecting it on a surface that's infinite, and it's a finite, in truth, phenomenon. And so the truth is you really should project it on something that's got a parabola, a half circle that is equidistant from a point, and then the projection will keep the pattern symmetrical the way it should be. Now you can still understand it goes in all these directions, so you can still understand what it would look like on the screen, and that is easier. But I'm just saying, if you want to know what it's doing mechanically, this is the right way to view it. So that's something they don't point out. And what becomes apparent is that it's just about the width of the slit. It's the distance between these 2 points. And so all I'm really measuring is that if I took a line and drew it from this point, this surface, this is in their math, by the way. This distance is a key variable in the math. This point, I drew a line, and I drew a line from this point. All I'm really doing is saying those two lines have a difference. It's the length of the slit. And at this point, those two lines are the same length. And all I'm doing is going through the changes you make to get from this biggest difference in the length of the line to this zero difference of the length of the line. And everything will be inside that finite space. So it's not an infinite pattern, it's a very finite pattern. And it's completely dependent on how many wavelengths are in here. So if there's 3 wavelengths in here, then there'll be 3 bars here, okay, proportionally spaced in here. And there'll be 3 on this side, so you always just double it. So it's whatever the number of wavelengths there are in the space, you double it and gives you how many bars of light there will be, where the centers are. And they'll be proportionally distant from each other, and it will explain the experiment. So now you get to the double slit is where it becomes more interesting in terms of that's where they say all this quantum magic happens. So that's why the double slit is so much more interesting to them. But it's exactly the same phenomenon. Nothing really new is happening. So in the double slit, you have a single impediment. That's the one they establish as your D variable, your distance, or your A variable, whatever they give it a distinction as. But anyway, that's the distance of the slit. I mean, the impediment now is the same as the variable of the slit, and they sort of ignore this and assume this distance to be infinitely small or very small, and therefore not creating any difference in the length. But obviously, if you understand the pattern, you get the most interesting pattern with slits that are proportional to the distance of the proportional in the sense that disproportional, asymmetrical to the distance of the slit, to the slits. So you're creating bigger differences in the distance. So the more open the slits are, the more interesting the pattern gets, in other words. And so the pattern you get is very different in the sense you get little bars of light, and then you get a nothing, and then you get little bars of light, and then you get nothing, and then you get little bars of light. So it's a very different pattern, essentially having 2 patterns stacked on top of each other, but in a way that isn't like what this single slit will create plus this single slit doesn't equal that, because it's not really about wave theory. So if I was to use waves can't produce this, okay? This 2 pattern problem. Single waves won't do it, because the real issue is going to be, again, it's just distances that are going to decide. So you have this distance, okay, the center impediment distance. Now that's creating 2 lines, as I pointed out before, of 2 different lengths. And then you have these 2 distances, okay, and that's creating 2 lines of 2 different lengths. And the length difference is much greater, obviously, for this one, so there's many more frequencies inside that distance. So where this one has maybe 6, you could say, this one has 30. And so what's going to happen is that if you make your little arc, and you got 6 notches, okay, for the first impediment. We'll just do it with 4. And so you have big blocks of light, all right, big sections, on, then off, then on, then off. Well, I didn't put that very centered. We'll do it right here, so that's the center. And then an on. So the hunks of light are large. So this whole area is lit with something called photon. All right, from these 2 surfaces. Those 2 surfaces create vectors, okay, that go to these places, and the wavelengths will match. Whoops, I'm doing it from the wrong. This one here, and then this one here. So the 2 lines. So if I was to make I can do this with string or something, right? So we can make this kind of simple. So you take a piece of string, okay, that is the distance, this total distance. So the center slit we know is going to create 2 lines plus the distance. Okay, so 2 lengths of this plus this distance. So you have a string that long, and then you just tack it to these 2 points, and then you mark this string, okay, with wavelength marks, you know, for how many wavelengths you have in that distance times 2. So you take this distance, you figure out how many wavelengths fit into it, and then all you do is multiply it by 2, put the notches on the string, and as you move the string, the notches on the string will be on the notch here, and then on a notch here, and on a notch, you know, in all the places that it'll match as a notch. And that'll work in terms of explaining, showing you exactly where the bands will be. So you can predict, by knowing the distance, you can predict exactly how many of these little on-off patterns you'll see. You'll see exactly the same number as the number of wavelengths that fit in the distance times 2. So really simple. So clearly just straight line vectors from those points. Not complicated. Alright, so that's for the first distance. The second distance is this wider distance here, these 2 sources. So you just think of the surfaces as sources. They're making sending bits in all directions. And there's only certain places where, like when you move the string, where the notch on the string matches. And when the notch hits that point, that means you're in phase. That means you have a full wavelength difference between these 2 lines, their length. Alright, so for the wider distance, you just do the same process. You count how many wavelengths fit inside the difference in the distance, this distance from this distance, and then that tells you how many bars there will be. So in this case there's going to be a lot more, so you know, draw them as little blocks, and so these are places that are also going to make a contribution of something called photon. Alright, so you'll have a lot more notches on the string. If you did it with string, you go notch, 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 notch. Now, these are places you'd hit. You're on the notch on the string. The notch on the string would be here. The notch would sit here. It would hit here. It hit here. Alright, so now you have this combination of this contribution plus these little contributions. And what's really happening in the experiment is the little contributions are added to the contribution from this one. So these are all just sources of pieces of photon. So as I argued before, there was, you know, you had to have 9 of these things for a human being to see them. I can make a simple argument, just say, well, if I break some of these, then you have a much smaller photon. But I can send 3 from here, and I could send 3 from here, and now I have 6 again. So let's say, and a human being could see that, because I sent 3 little bits that got broken off here and 3 little bits from here. And this is really an argument about phase. So the argument is that what happens is they have to be in phase plus the bits have to be there. So they have to not only show up, but they can't be out of alignment. So if I add 2 things that are out of alignment, I'm not going to get the proper frequency, and I'm not going to see a photon. But if I send 3 bits from one photon that were these 3 bits, you know, and then I sent out, you know, bits from another photon, it can create these 3 bits in time, and now I've connected those 2 different events into one photon. So the point is that it just adds up. So if you say this is, you know, 1/2 of a photon, and then these little bits are all 1/2 of a photon, then at this location I'll see a photon, and at this location I'll see a photon, at this location I'll see a photon. So they're just adding. So if I add more slits, you can see exactly the same process. So I could just add more slits by just making these lines further and further apart, making smaller and smaller little notches. Okay, so now I have an even longer one with 3 slits, and then I have even smaller ones with 5 slits and 10 slits. And the more slits I add, all I'm doing is stacking contributions. So the first pattern creates this big area of potential photon. Then the second slit creates these areas of potential photon. Okay, and they're just piled on top. And then the third creates another smaller little areas that could be a photon. All right, and you can just see that there would be an alignment thing. So at every certain location, so a diffraction gradient that has many slits very close together is creating pattern on top of pattern on top of pattern, and you're just saying how many of these are in phase. That is, this one's on top of this one is on top of this one, so that's lined up. Here you only have this contribution, so it's only, you know, that much photon. It's not enough to make a photon. Here you have these two, you know, well, here you're lined up again, and this one. So again, the more slits you have, the more you're lining up, and so this pattern, the place where you get enough photons, enough contributions to make a photon you can see, becomes further and further apart. So as you add more slits, the distance between the real brights gets further and further, because there's the place where they all create a pyramid. That is, the little one is right in the center of the second one, is right in the center of the third one, is right in the center of the fourth one. The place where they create a perfect pyramid, okay, where they're all in phase, moves in terms of the pattern, where they all line up, where they're back on resonance, you could say. So they they'll line up only in certain locations where everything will be in phase. From every single location, the line difference is in phase. Every single location to this location is in phase. That's the place you'll get the big spot. And you'll get another big spot over here, another big spot over here, and that's all you'll get. But anyway, it's all calculable exactly how many bars there are. And you know the bars just have to go over this distance. So we're just doing basic algebra, you know, your basic, what do you call that? The basic geometry of converting this diameter distance into a circumference distance. And over that circumference is where all of the wavelength information goes in. So the mathematics is rather simple. And it works for every single version of the double slit. So all you're really doing is saying how many wavelengths, you know, lambdas, inside of the distance d, and then all you're going to do is put that number times 2, all right, and put it over this parabola, this half circle. So you're just doing your pi times the diameter. Sorry, we got d in diameter, but anyway, and I'll tell you how many there are going to be. And then you just subdivide them into that space, and you'll know exactly how far apart they are, and where they're located, and why there's a contribution, because both line up. So the double slit pattern, these empty spots, are created by the empty spots here between the big pattern. So where the big pattern is off, even though there's a little contribution, it's only a half a photon, so 1/2 photon isn't going to be seen, and then there won't be any. It's only a half photon here, so it won't be seen. It needs the contribution from the first distance plus the second distance. Is the only place you'll see a photon, is where both of those are on phase. Where one of them's out of phase and the other one's on phase, there's no photon. So it really just has to do with how much light gets through the slits and all this other stuff. But I mean, that's the basic mechanics of it. There's no destructive interference in space. All you're really doing is taking photons that have a rather large shape. You're sending that photon into a slit. Some of the photons get broken off. Some of these little bits break off. They hit the surface, and then some of them on the surface, well, I should draw that bigger, just to give you the mechanical reasoning. So this diagram works. The math is one set of math. They're all the slit arrangements. It explains all of it. There's no infinite patterns. There's no complexity to the pattern. It's actually incredibly simple. All you have is 2 distances. So let me just reiterate that the double slit just has 2. There's 4 point sources. There's no 2 waves going through space interfering. That's not happening. That won't create the pattern. What will create the pattern, okay, what does explain the pattern, is you have 4 point sources. You have this, You have this one, you have this one, and you have this one. And those 4 point sources are only in phase in certain locations, where all 4 of them are sending pieces that are in phase. And that's why you have the pattern you have. And the only contributions really being made are this. Obviously the distance of the center impediment, that's where the first 2 surfaces are. Obviously a wave is not being created there. And the other distance that's relevant is this one. And obviously a wave is not being created here with a hole in it. So to draw waves that would represent the actual outcome, you'd have to have one of the waves here as a point, and you'd have to have the other wave here. And that's obviously, there's no way to make that mechanically make any sense. Water clearly wouldn't do that. So it's nonsense. Alright, so the mechanism of the experiment is, so here's your slits. I'm proposing that there's electrons on surfaces. And what happens is as the photon comes in, right, it has a pretty big polarization. There could be, like, if the polarization is just like for the the small single slit pattern, the uninteresting one, obviously the polarization is going to be half of this distance. So the photon is kind of big. You'd only fit 2 in there at once. So obviously lots of the photons will hit the surface where their wave polarization, if you want to think of it as a wave. Obviously I'm saying our wave is a silly notion, but anyway, if you can't let go of it, you can understand that yes, part of the wave is hitting the surface and it's destroying some portion of your photon. And the portion that's getting through is going to be hitting these electrons. And when it hits the electrons, it scatters. And it scatters in and then reflects and scatters, but it doesn't really matter. The idea is this point source creates scatter. Okay, and when it hits an electron, it can go in any one of these directions depending on how much tension the electron is in. So depending on how the electron is arranged, it will push the photon in a different direction. And so that's essentially dictating where the light's going, the bits of the photon. So pieces crash into the wall, and that means you have your photon, and some bits will be destroyed by crashing into the wall, and then some bits will be sent in different directions. Okay, that one will go this way and that one will go that way instead of going straight this way. And then all you're really doing is you're throwing all of those pieces at this wall, and in some places all of the pieces combine, pieces from one combine with pieces from the other, and now they restore the phase, this distance between them. And when you add the pieces and you restore the phase, you end up with a photon. See, the pieces are going from here to this location. I'll go to the dark spot. I actually did go to the dark spot, which I shouldn't have done. So let's say this is a dark spot. Obviously, pieces from here are going there, and pieces from here are going there. But the problem is they're out of phase. That is, the notches are in the wrong places. So you can't reconstruct the photon because now the frequency is broken. You have a piece that's too close to the other piece, and then it goes back. So it goes this frequency, and then it's really close, and then it's this frequency, and then it's really close. That isn't going to be seen as a photon. So the energy is still going here. It's just not in a form, the quanta, that can make a photon because it's out of phase. And then when you put it back in phase here, then you can get a photon. So there's just as much stuff going here as there is stuff going here. It's just this stuff's out of phase and this stuff isn't. And that's the real truth of it. There's not a different amount of anything. Now they claim that there's some experiment where they have the 2-slit experiment, but it's again just a claim. There's no experimental evidence that I can find anywhere demonstrating a well-performed experiment demonstrating it as a fact. So they claim that you have one slit open and there's light going to a location here, and that if I open another slit here, that the light that was going here doesn't get there anymore. Now, they don't have any experimental evidence demonstrating that. What the evidence demonstrates is that you have locations. When you open one slit, you have a blob of light, right? Because we're opening small slits. Okay. And then when you open a second slit, you're sending a blob of light to essentially the same location. But that's not what actually happens in the experiment. Again, it's just point sources. And so this whole thing, you got to always remember that this source is just a millimeter across. And so, the images are going to be really right on top of each other. And so what actually happens is these spots just get brighter. I mean, if you have this as the underlying pattern, these little bars just get much brighter. The places where the second slit introduces these further sources, the further away sources, those just brighten these spots. These spots never get darker. Okay. There's no evidence that that's truth, that this spot gets darker and this spot gets lighter. There's only evidence that this gets brighter. So obviously it looks like, could look like, this is now darker because this is so much brighter. And that's really all that happens. So it's really the nail in the coffin evidence that there's no need for wave theory. It doesn't even work. Again, like I said, it'll work for a single slit. This idea of vectors from point sources, and these point sources are the surfaces. That's where the action happens. That's where the math calculates correctly the locations, and so it's just about adding locations to create a photon. So there's no destructive interference. There's just constructive locations where you constructively recombine the pieces to make the photon back into something we can see. So there's just constructive reconstruction. There's no destructive anything. Alright, I think that should be enough on the subject. So I just wanted to keep this a standalone video on this one single subject. And this, in my opinion, nail in the coffin. Waves first don't work for the 3 different experiments. You have to modify the formalization to make them work. And so this one mechanism works for all 3, explaining why the pattern is what the pattern is. And so clearly strong evidence of a particle theory, not a wave theory. Very strong evidence. Oakley doke. That should do, and such. Comments welcome in terms of citations to any experimental evidence that says otherwise.